Today we're going to cover 2.3 on correlation. Some objectives for 2.3 on correlation. After this lesson, you should be able to estimate the correlation between two quantitative variables from a scatter plot. You should be able to interpret that correlation, and you should be able to distinguish correlation from causation. So make sure that you've started a new topic in your notes on correlation. In the previous lesson, we used direction, form, and strength to describe the association between two quantitative variables. In this lesson, we will quantify the linear relationship between two variables. Quantify means to assign a number that will describe that relationship without using words. So all of that direction, form, and strength, we will sum up with this number that we call the correlation coefficient. Correlation coefficient is represented by the lowercase letter r. All right, some characteristics of correlation, and you're definitely going to want to write this down. Correlation always falls between -1 and 1. If we write that using math, that is in between -1 and 1. Correlation is somewhere between -1 and 1. If the relationship is negative, that means r is smaller than 0. If the relationship is positive, that means r is greater than 0. If you get that r equals 1 or r equals -1, then that indicates a perfect linear relationship. In other words, all of the points fall exactly on a straight line. The weaker the relationship, the closer r falls to 0. So let's look at r on the number line. So typically we put arrows on the end of a number line. We don't for r because r stops at -1 and 1. It's a boundary in between those two numbers. 0 is in the middle. 0 indicates no correlation at all. -1 means a perfect straight line with a negative slope. +1 means a perfect straight line with a positive slope. Most relationships fall somewhere in between this. So for example, 0.5, I like to use quarters to help me figure this out, is halfway in between 0 and -1. -0.25 falls halfway in between 0 and 0.5. Just like this is 50 cents, this is 25 cents. That means this is 75 cents. Again, halfway in between 0 and 1 is 0.5. Halfway in between 0 and 0.5 is 0.25. And halfway in between 0.5 and 1 is 0.75. In between 0 and 1 goes all the way from a weak relationship to a progressively stronger relationship. It works the same in the other direction. Weak starting at 0 to a progressively stronger relationship. So this is weak, this is strong. So let's look at some actual examples with some scatter plots. Here we have a correlation of 0 right here. This one right here is a correlation of 0. That would fall right here, which means there is 0 relationship. Now, it can be hard to see with those weaker relationships. This has a correlation of -0.3, which means there's a weak relationship, but it is somewhat negative. If I were to draw a line of best fit, it goes somewhat in that direction. This one's a little bit stronger. The dots are a little bit closer together. You can see the trend. So it's a moderate relationship right here. So we would say this one is weak, this is no correlation, and this is a moderate. None of these are very strong. If I have a correlation of -0.99, that's right here. That's very strong. It's not perfect, but those dots almost form a perfect straight line. -0.7, it's about right in here, that's moderately strong. Not very strong, it's not a perfect straight line, but it's moderately strong. A correlation of 0.9 right here would be considered strong. Again, it's not a perfect straight line, but we can definitely see that there's a relationship between those two variables. I would keep these pictures close by where you can reference them. You don't need to draw a sketch of them, but you can if you want to. You can always just go back and rewatch this video. So let's talk about some facts about R. We want to identify the true statements about the correlation coefficients R. So here are our options. The correlation coefficient is not affected by outliers. A correlation coefficient of 0 means that no relationship exists between the two variables. If two variables are negatively correlated, when one variable increases, the other variable also increases. When the data points in a scatter plot are randomly scattered, the correlation between the two variables is weak. The value of R ranges from -1 to +1, and the absolute value of R describes the magnitude of the association between the two variables. Essentially, without worrying about the sign is what that means. How strong is the association? Go ahead and see if you can put a check mark next to the ones that you consider true. Here's what you should have chosen. Correlation coefficient is not affected by outliers. That is not true. The outliers can definitely skew your correlation coefficient and make it weaker when in some cases it should be stronger. For example, if you had a perfect straight line of dots and then one outlier, that's going to make your correlation coefficient be smaller than 1 when the rest of these fall along a perfect straight line. A correlation coefficient of 0 means that no relationship exists between the two variables. That's not necessarily true. If your dots are in some weird shape, that might give you a correlation coefficient of 0. There is a relationship, but it's not a linear one, and so we can't use correlation coefficient for that. If two variables are negatively correlated, when one variable increases, the other variable also increases. Well, that describes a positive relationship, not a negative relationship. When the data points in a scatter plot are randomly scattered, the correlation between the two variables is weak. That is true. The value of R ranges from -1 to +1. That is true because we said that R is in between -1 and +1. The absolute value of R describes the magnitude of the association between the two variables. That's true. Whether you have -0.9 or +0.9, those are both strong relationships. So that describes the magnitude of the association without worrying about the sign. So you should have chosen the last three there. Let's look at an example now. Manatees are large, gentle, slow-moving sea creatures found along the coast of Florida. Many manatees are injured or killed by boats. Here is a scatter plot showing the relationship between the number of boats registered in Florida in thousands and the number of manatees killed by boats for the years 1977 to 2015. So let's ask ourselves some questions here. Which of the following is the most likely value of R? Before you answer that, you need to consider some other questions. Is R greater than 0 or less than 0? In this case, R has to be greater than 0. There is some sort of linear relationship here, and it's positive. Is it closer to 0 or closer to positive or -1? Well, it looks like a pretty strong relationship here, so it's got to be closer to 1 instead of closer to 0. What do you think the correlation coefficient is here? You should have said that your correlation coefficient is 0.94. It has to be positive because it has a positive correlation. It needs to be closer to 1 than 0, so it can't be these 0.34s, that's too weak. There's definitely some correlation, so it can't be 0, and it can't be negative. That would mean the dots were going in the other direction like this, so our only option there is 0.94. So a word of caution, a correlation close to +1 or -1 doesn't necessarily mean that an association is linear. For example, the scatter plot below is clearly nonlinear. This makes this curved shape here. The correlation for this, based on the computer work, is 0.93. Correlation alone doesn't provide any information about form. To determine the form of an association, you must look at a scatter plot. Remember, correlation is only valid when our data shows a linear correlation. Correlation is a good way to measure the strength and direction of a linear relationship, but it has its limitations. This is important, and you're going to want to write this down. Correlation doesn't imply causation. In many cases, two variables might have a strong correlation, but changes in one variable are very unlikely to cause changes in the other variable. Think about it. Will a change in the revenue from skiing change the number of deaths from tangling? These are two different things. For some reason, these are positively correlated and pretty strongly. So yes, we would say that there is a positive correlation here, and it's a pretty strong one. But this is not causation. One of these things cannot cause the other. They are correlated in some way for some reason, maybe based on some other variable, but we cannot say that one causes the other. That is not what that means. Let's look at another example of this. Does chocolate make you smarter? Most people love chocolate for its great taste, but does it also make you smarter? A scatterplot like this one recently appeared in the New England Journal of Medicine. The explanatory variable is the chocolate consumption per person for a sample of countries. The response variable is the number of Nobel Prizes per 10 million residents of that country. Excuse me. So here we've got our graph. We've got our explanatory variable on the x-axis. We've got our response variable on the y-axis. We're graphing these two separate variables and seeing how they're correlated. They are correlated. Would you please right now interpret the correlation of 0.791? What does that correlation of 0.791? Think about what it means that R is positive. Think about whether that means it's strong or weak or moderate, and go ahead and interpret that now. You should have said that the correlation of 0.791 indicates that the linear relationship between chocolate consumption per person and the number of Nobel Prizes per 10 million residents of that country is moderately strong, and positive. It's moderately strong and positive. I've interpreted the correlation. I have not said anything about whether or not chocolate causes more Nobel laureates to happen. So let's talk about that. If people in the United States started eating more chocolate, can we expect more Nobel Prizes to be awarded to residents of the United States? Explain. Go ahead and do that now. The answer is probably not. Although there is a moderately strong positive correlation, an increase in chocolate consumption is not likely to cause more Nobel Prizes. So here's the answer that you should have put. You should have said probably not or no in some way. And your explanation is an increase in chocolate consumption is not likely to cause more Nobel Prizes. Here's what's happening. It is likely that both of these variables are changing due to other variables, such as per capita income or education level. If a country is rich enough to afford more education, it is also likely rich enough to afford more unnecessary expenditures like chocolate. Here's another example. Did pirates keep us safe from global warming? Between the 1800s and today, the number of pirates has decreased from about 35,000 to under 1,000. During this same time period, global warming has increased the average temperature from about 58 degrees Fahrenheit to 61 degrees Fahrenheit. There is a strong negative correlation between the average global temperature and the number of pirates in existence. Does this suggest that global warming is to blame for the near extinction of pirates? Go ahead and choose your answer there carefully. You should have said no. There is no way that pirates kept us safe from global warming, so that narrows it down to these two. It is unlikely that the increase in average global temperature caused the decrease in the number of pirates. Correlation does not imply causation. The other option was, no, in order to show causation, we would need to know what part of the world the pirates came from. Maybe the pirates migrated towards the poles as global temperature increased. This explanation does not make sense, although the no is correct. We know that pirates did not migrate toward the poles, so your answer there should have been the first one. All right, after you finish this lesson, you should have been able to estimate the correlation between two quantitative variables from a scatter plot, interpret that correlation, and distinguish correlation from causation. If you need to re-watch the video to take a look at some of the examples, you're more than welcome to. This will be available on Edpuzzle from now on. Have a great day.